Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors, Video 5, Unit Vectors. Unit vectors will be critical in our study of vector calculus as we move throughout this course. So it's kind of important to define what a unit vector is and how to get one when we don't have one. So the definition is pretty simple. A unit vector is a vector whose magnitude is 1, whose length is 1. So we're going to look at two things. Answer the question, are you a unit vector? And the other thing we're going to look at is finding a unit vector in the same direction as a given vector. But let's tackle the first task first. Is the vector 5/13, 12/13 a unit vector? Depends. Is its magnitude 1? Let's find out. To find the magnitude, remember the symbol for magnitude is absolute value. To find the magnitude of the vector 5/13, 12/13, we simply have to find the square root of the sum of the squares of its components. So in other words, we have to do a lot of arithmetic. But it's arithmetic, and this is calculus 3. The arithmetic shouldn't bother you. If it does, come talk to me. To square 5/13, we square both sides, and we get 25 over 169. If we square 12/13, we square both sides and get 144 over 169. We're adding fractions, we need a common denominator. Luckily we have one already. If not, we would have to get one. 25 plus 144 is 169. 169 divided by itself is 1, and the principal square root of 1 is 1. I say principal in case there's any nitpicky people watching this video, because 1 actually has 2 square roots, but the principal square root is 1. And the magnitude is 1, which means the answer to this question is yes, you are a unit vector. Think of it this way. If I located the point 5/13, 12/13, it would lie on a unit circle. 5/13, 12/13 would be about here somewhere. How do I know it's on the unit circle? Because I know the magnitude of that vector is 1. And every vector formed by using the origin as an initial point, and a point on the unit circle as a terminal point, must have a magnitude of 1 because it's a unit circle, radius of 1. What about this guy? Is 2 comma negative 1 comma negative 2 a unit vector? Your instincts might say no, the components are too big, in which case you would actually be correct. But to be definitive about it, you should find the magnitude of this vector. The square root of the sum of the squares of its components. Now be careful, some of the components are negative. That shouldn't bother you, but I can't tell you how many people at this level don't square negative numbers correctly. They know how to square a negative number, but they put it in their calculator, don't put it in parentheses, and so the negative doesn't get squared. Don't do that. 2, negative 1, and negative 2 are all going to get squared. So that's 4 plus 1 plus 4. That sum is 9, the square root of 9 is 3, and that's not equal to 1. And since that's not equal to 1, this is not a unit vector. But I'm not done with this vector yet. In a lot of situations, we're going to need to find a unit vector that is in the same direction as a given vector. So the follow-up to this is find 2 unit vectors. Actually, let's take off the word 2. Find a unit vector in the same direction as 2, negative 1, negative 2. In other words, if we were to locate the vector 2, negative 1, negative 2, and I'm just going to throw it up here at random. This is actually pretty common to do without getting out R3. Just throw a vector up there and say, here's the direction it is. The reason it's allowable because nobody said when you're looking at R3, you have to be standing on the x-axis looking at the origin. You can move anywhere in space and look at a vector from any perspective. So without a frame of reference, it's okay to just draw a vector at random and label it whatever its components are. So how are we going to find a unit vector? Well, think about what we're looking for. We're looking at a vector for a vector that's in the same direction, but the magnitude is equal to 1. Wait, it's in the same direction. When we take the scalar multiple of a vector, it preserves the direction. It might point it backwards, but it preserves the direction. So our plan of attack is to find the correct scalar that would scale that down so that its magnitude is 1. What do you think that scalar is? I'll give you a hint. Right now, its magnitude is 3. I want its magnitude to be 1. So the scalar we're going to use is 1/3. In general, to find such a unit vector, you multiply by the reciprocal of its magnitude. Multiply by the reciprocal of its magnitude. This is standard fare from this point forward. Now we've already found the magnitude of this vector and it was 3. So our answer is going to be the reciprocal of that, which is 1/3 times the original vector, 2, -1, -2. It just dawned on me that there's a reason I didn't do, I know you can't see my list over here, but originally I had unit vectors further down the list of things to do. And I thought, well, let's do it now since we're talking about magnitudes, but now I remember why I put it further down the list. We haven't talked about how to do vector operations in component form. We haven't talked about how to do scalar multiplication in component form. So I gotta jump ahead just a little bit and tell you that you do exactly what you think you do. The way you find a scalar multiple of a vector in component form is you multiply the scalar times each component, almost like a distributive property. 1/3 of 2 is 2/3, 1/3 of -1 is -1/3, 1/3 of -2 is -2/3. This has the same direction as the original vector because it's just a scalar multiple of it, and its magnitude is 1. Now we didn't verify that its magnitude is 1, but think about what would happen. We would do the same thing up here, but we would do it to this. All of these would be over 3, which means when I square it, they would all be over 9, which means this would be over 9, which means it would become a 1, and the square root of 1 is 1. So it actually is the correct answer. It's actually not the only vector, it's not the only unit vector, and that's the same direction, if you will. Actually it is, but there's also a unit vector in the opposite direction. The unit vector in the opposite direction would just be the negative of this. -2/3, +1/3, +2/3. So for any vector, there's always two unit vectors pointing in the same direction. One might just be going backwards from the other. All right, so that's what I get for rearranging the order of the videos, having to introduce scalar multiplication in component form out of nowhere, but I get the funny feeling you all knew about scalar multiplication anyway.